Hey guys, welcome. Today is about the bridge optimizer once again. And I thought it would be good to have another video, but also a separate video, to look more into what the script builder is doing. So not everyone is really interested in really digging deep into the rabbit hole, but I thought it would be maybe interesting for one or two or multiple of you guys. So, let me go into it. So what I did is I created this GitHub repository, and you can pull that, and you have that then in your Visual Code Studio, Visual Studio Code, or whatever IDE you're using. And well, it's the same code. I didn't change anything compared to the first video. And I want to walk you through the script builder things and how you maybe also, well, I covered it in a lot of videos, how you work with Altair in terms of TCL scripting, but maybe a little bit about the variables and stuff like that. So to jump into it, I have a Hyperworks, Altair Hyperworks 2021.2 window open and things where we have commands. And yeah, I should maybe also open the command TCL file, the corresponding command TCL file. Let me quickly do that. Yeah. So this is the command TCL file, which is located in my documents folder. And this is where we're at. So if I do something like create node 000, bunch of zeros, this should be reflected here. Yes, and indeed it is. All right, so setup is complete. So let's jump into the code. I will, for the sake of simplicity, go to my main class. And by the way, I'm sorry about it's not tidied up. So there should be different packages and a main class, which is obviously the main class. And there's a lot of documentation also necessary for me to do in the code. But I will just use the main class to work you through the things the script builder is doing. So the first thing is initializing the script builder. So it's just making a new instance of the script builder, and I transfer this mesh into it because the mesh serves as a placeholder for different kind of things. So for example, in the script we will then be using, for example, the neighbor distance threshold, or the length or the height, and also stuff like the matrix. And so yeah, so basically here it tells you have a length, height, and spacing, and your neighbor distance threshold. We covered that in the last video. So this is the maximum length of the beam, or the maximum beam length. Yeah, and those variables will get put into the mesh here. And what this is doing is it assigns the variables here. So the length and the height is currently meant to be number of dots. So you see that you have the mesh in it. Here it is called n.x, n.y, which is the grid size in x and y, and the spacing. And those are integer values, and this is a float value. So this is assigned to the class or the instance values. And then you have this matrix, which is more or less just a list of lists. So let me show you what I mean, because I also made a print matrix method, so you can easily show what this is doing. Yeah, let's see if that works. So for just debugging purposes, I will launch a Python shell here, and then we have maybe we just make the line, copy that. That's maybe a little bit faster. We'll just be using the different values here. Just copy paste them here. And then the error is a little bit fortunate. So length. Let me do that other differently. Hope this is working. Yeah. So mesh is not defined, so we have to import mesh. Why is this not working? I think I'm in the wrong folder. Yeah. Let's do it again. And use this. So this is just a little setup for me to show you what I mean. Spa is not defined. Ah, okay. It has selected everything. Right? Come on. So, mesh is imported. Now I can make that. So, what I did here is I executed this command here. And now I can, for example, just do a mesh.print, and there's no autocomplete. But you see it here, there's this method called print matrix. And this will just print our grid. If I call it correctly. So you see here, it just does these things, or this plot here, where you have for each row, yeah, it's basically the grid. And I initialize it with ones, because if I don't want to have active grids here, I will put them to 0. So this is the basic idea. Make a grid with ones in it wherever a node is usable, right? Okay, but enough of that introductory stuff. Let's jump into the juicy parts, the script builder of the Hypermesh. So script builder gets initialized, right? So you have script builder initialization and the mesh is transferred. So this will initialize it. So you have a list of self.tcl commands, and then you have this method from Hypermesh starter, but this is really not really a thing here. It's just giving you back a empty list, and you have the assignment of the mesh instance to a variable placeholder in this instance, so that you can, with different methods, also access this instance, right? So nothing fancy happening here. If we execute this, I must be sure to import script builder first. Now I can do that. So script builder. What should we do? There's this TCL commands, right? TCL commands. Print. So you see, it's just an empty list, right? Okay, now we get into the methods. So the first thing which is happening here is write TCL create nodes. And this is, first of all, initializing a separate list of lists, or you can also say a separate grid, which has the IDs in it. And we will look into that in a bit. Maybe I will just also also introduce a method which prints the IDs. So we have this this print matrix method, which is good, or which served us good. And we make another method here with def matrix node IDs. So we'll see about this in a second. All right, let me first code this thing. So self.IDs. IDs. Sorry, I forgot how this is done. self.mesh.ids. So there should be a thing. So for I in range, so for every row in the length of the matrix, but the matrix is a list of lists. So what exactly? Ah, this is in the mesh. So self.ids. Oh god. The thing is not really good here is that those variables are not really declarated. And I I edited the wrong thing. So we want to print the IDs. So I changed this to IDs. And IDs is really not known here because it's not declarated anywhere. So I will make something like this. IDs equals a list of lists. The same thing as the matrix. Oh god. Right. So now I'm supposing this should work. Yeah, so it recognizes this IDs, right? Now, as I have initialized this IDs, no, I did not. So the script builder has different methods. And also there's no autocomplete here, but going back to the main class here, the main, I'm sorry, this is a little bit confusing, but you'll get the point on when I run this. The first method which is executed is this write TCL create nodes. And the purpose of this method is to just add the TCL commands for creating the nodes, right? So, and while doing that, you have to be sure to have your IDs fixed. This is rather important later on for assigning the nodes to the elements, or rather for creating the rods, because you have to define from which node and to which node you want to define a rod. You will see that in a minute, but for me to be able to tell which node has which ID, I have to assign it here. Assign it is maybe the wrong word. It's rather so that I create the nodes in a specific order, and by creating them, I know which node has which ID. This is not the perfect way. Maybe a better way is to create a node and then assign an ID to it. But there also it's not so perfect either, because you don't have the whole control about the data structure. Because a command in Hypermesh actually may change the node IDs, and then you will not be able to see that. So for that reason, I also thought maybe to do it just like creating the FEM file for myself, therefore, and then importing it, also a possibility. But so you see, I'm just putting out ideas. But the way it is put here is I start with the ID counter to be 1. And now for x in range of the self.mesh.matrix 0. So this is for each column. That's why it's called x. And for each y, this is the rows. And that's only because you saw the print in... sorry, it's not. You cannot see it here. Oh, my Python went away. That's then rather unfortunate. Whoa. Okay. Here. That's just for the grid. So you see rows or list of lists. This is a row. It's a bit strange that there are no closing brackets here. I don't know about that, but you see rows and columns, and the columns are the x value, because if you have this a grid, you would rather have this dimension to be the x dimension and this dimension to be the y dimension. So the counter goes x for the length of the row and y for the length of the whole rows. So the length of a column. And that is okay also for disabled values, because disabled grid points will be a 0. And this is the if question here. So I'm only creating a node if the matrix has a 1 at a particular location. So if there's at any point a 0 here, it will not create a node there. Alright, but if there's a 1 here, I want to append a command, and this is the command. You see it's an F string, which allows me to put in variables here with the curly brackets. Is this the curly brackets? Yeah, you know those brackets, right? And here I have x time the self.mesh.spacing. So x times 0 means 0, 1 is 1 times the spacing, 2 is 2 times the spacing. You get the idea. And the same thing for y, and then a 0 for the set component, and there are 3 another zeros. This is just because of the Hypermesh command. I don't know really about them. It's a system ID and whatnot, but you can look that up in the help. And I also assign in the order of creation an ID counter to this particular location, but not in the matrix, but in the IDs list of lists. And then I count the ID 1 up because I created a node, so the ID is counted 1 up. And this is the create nodes, right? So doing that, script builder. Sadly, there's no autocomplete, but maybe I just copy it here. So script builder, and I will execute this method, and now I should be able to, because we created this method, this print method for the IDs, that you can see what this is about. And I'm not sure if I have to restart it. I hope not, but could well be. Could well be. So we have a mesh here, right? Yeah. So yeah, I'm definitely sure we have to restart it. Yeah, it has nothing like this. All right, so restart that, because those class variables are, or these methods are initialized at the beginning, and so you have to restart it. And so basically we have to execute everything until this point where we were. So until here. And this should be easy, but let's make sure we have the imports fixed. From mesh import mesh and import script builder. Capital B. Right, now I paste it in. So now I have executed the lines, the method with the commands, and now I should be able to mesh.print, what was it called? Node IDs or something like that. Matrix node IDs. Right, so. And now you see the order of the creation. So you see it's going like this. It creates 1, 2, 3, 4, 5 up. And those are the node IDs. So let's print the TCL commands that we can see if that's correctly done. So for line in mesh, no, script builder, the TCL commands, print intended. Oh. So you see, you have now a bunch of lines, which I just printed it here. But you can execute them rather easy in Hyperworks by just pasting them into the TCL console. And by doing so, you will have this grid. So this is first basic step. Last one have to be executed as well, because the last sign here, the new line symbol, which is not available or seen here, that's why the last command is not executed. But having now turned the IDs on, you can do shows you exactly exactly that not. Here it starts with 1, here it starts with 2. Why is that? Because when I opened the Hypermesh window, I just created a node. And you see why this is a little bit dangerous. So if I do this once again and copy my commands here once again, now it should work. And we make sure it does by once again showing the numbers. So you have to be careful about this. And that's why I also like to record something like that, that you can see what also can go wrong here. And maybe don't fall into the pitfalls. I most certainly fell in multiple times. Yeah. So learn from my mistakes, please. All right. Now I think this should be clear, right? So nothing fancy. TCL create nodes, just create based on a list of lists, create the nodes, assign an ID to the same column and row of a matrix. There's nothing fancy here. So the next thing is a little bit more complicated. It's creating the elements. And here it's called TCL create rods. And you have to give in a neighbor distance threshold and a spacing. Now let's see what this does. So first of all, what is done here is it creates a... first of all, it changes the element type, that the 1D elements you want to create later on will be rods. And then you want to create a material. And you also can see the name of the material. You could parameterize it, but I did not see a point in here to do that. And I don't think this is even necessary. But then you also set some values here for the Young's module, the Poisson ratio, and the density. Density is important. Don't skip the density. Why is density important? Because of the mass. You maybe want to minimize the mass, and if you don't have density, you don't have mass. Well, sure, you can do the volume, but it's rather nice to have a mass, put it out in the out file, and your mass savings and stuff like that. So don't skip the density. Then it creates property for the rods. You see card image p rod. It's called property 1. It creates a beam section collector, a beam section. So this is the cross section, and it defines that to be just a rod. And I had a problem of when I played around a little bit with the spacing, right? I had the problem that the cross section, the diameter of the rod was way, way, way bigger than the distance between 2 points. So what I thought would be you have this shortest beam length, which is the spacing in here. You remember I gave the neighbor distance threshold and the spacing. And the spacing actually here is the shortest beam length because, well, it's assuming constant spacing with the grid, but this is a given for the approach I'm taking here right now. So the shortest beam length is in fact 1 grid space. So the diameter is dependent on that, and it's 1/5 of the shortest beam length, which is just a basic value I'm putting in here, but this prevents having the trouble of having really, really large circular tubes, which are very short in length, which you should not do. All right, then you have the clear mark beam section. I'm again not sure if that's even necessary, but then you select, you assign the different properties to the beam collectors to the property to the component, material to the property, and stuff like that. And now here comes the juicy part. So first of all, you see that there's a links already drawn. This is the thing, and I'm sorry I have not my Wacom tablet here. I can show it to you with the grid. This is the thing. If you want to create, you go from node to node. Now let's see how it works first. Then I will explain what this is. So for X in the range of X, for Y in the range of Y, if the node is valid, then the ID is right, the ID of the node. So you would start with node ID 1, ID would be 1. And now you want to search for neighbors. This is a separate method, which just lets you go into finding all the neighbors within a certain distance. I started with just using all the neighbors north, south, east and west, sorry, and all the sections here as well. So you have 8 neighbors, 8, 3, 6, 7, 8, yeah, 8 neighbors of one particular node. And I thought maybe then, yeah, in the bridge constructor, you can also make a connection from here to here, for example, and this would never be able to do. Just could go here and then here. So I thought, okay, maybe it's better to put in a distance threshold, which is exactly what this is doing. So this is just using a threshold, and you have XY. This is the grid location where you're at. And XY is not really in distance, right? Maybe I will change that in the future, but this is right now coordinate indexes, which are used to go into the matrix and find the particular node. All right, and just really going quickly into here, if I'm able. I'm not able. I don't know why it's not. Control click should work. No, let's search for it. All right. Self.mesh. Okay, maybe it's because that. So here there should be, yeah, this is the method, and this is just going through all values. So for x1 and y1, if the node is active. And now I don't want to have the same node again. So, you know, you have the node 1 and you don't want to have the node 1 included into the neighbors because it's the same node. And then you calculate the distance, which is just a Euclidean distance. I will not go into that. And if the distance is less than the threshold, and if the ID of this neighbor is not in neighbors, this is just a list here. This is just to ensure that there are not duplicates, but rather this is not possible. But it's a good check to have it here. And then neighbors append. You put into the ID into the neighbors. So basically, what this is doing, it gets you all the neighbors within a certain threshold, or Euclidean distance. And now for neighbor ID and neighbors, now we come to the juicy part of neighbors already, or links already drawn. It could well be that you have started here and you found the neighbor 19 because it's in the threshold, and you make a link between here and here. A link is made by just using that command here. See, that's really easy. It's rod, then the start ID, which is the ID of the node, and then the neighbor ID, which is the ID of the neighbor node. And then you just assign a property here. This is also very bad because it's property 1. Maybe include that as a variable. That would be an instant improvement. Because if you change that, this will not longer work anymore. I will do that in a minute. Now you create from 1 to 19, right? So we can make that here. Well, how do we do that? I will explain it and then we will see how it goes. But the thing is, you're creating from 1 to 19 and then later you are at the node 19 and you're searching for neighbors and you find all those neighbors, for example. And 1 is also in there, but a rod between 1 and 19 already existed. So you don't want to double create it, right? And that's what this is preventing. So with each link which is drawn here, so you append a command and links already drawn append a tuple of ID and neighbor ID. And you're checking that it's not in there already by ensuring here that the tuple ID neighbor ID is not in this link already drawn, but this is the thing you want to do. So this would be 119, but actually if you're at node 19, it's 19.1. So you have to make sure that 19.1 is also not. That's why and. So ID neighbor IDs should be not in links already drawn, and neighbor ID should be not in links already drawn. And if that's the case, then the command will be added, otherwise it will not. Alright, so that was me explaining that. And now let's just see how it's done here. So it's just one. Does it make sense to show that? Yeah, I think for better understanding it does. So I will execute the command here with the rods. This should be right, and now I just print the lines as well. So again, and you see all the different kind of rods which are created, and I think. Yeah, I think that we run into a command terminal threshold. Then let's make it differently. For I in range 200. Oh. Okay, this worked, but I think we should increase the threshold. Let's hope for the best. Yeah? Yeah. Because what I wanted to have is this part where the property is created. Because then I can show you what the command is doing. So it starts here. So we're going into here and just pasting it here. So you see in the model there's a beam section collector. And you have this beam section which has 0.25. And in this case, the spacing is 1.25. Now, I can create now a rod from 1 to 19 and take the property 1. And this will just make something like that. And if I happen to have 19.1 as well, you would have 2 elements here, both connecting the same nodes, but that's not what you want, and that's prevented by the command. All right, I think that's okay now. So what's left to discuss? We have the right TCL and loads. I think I covered that a bit in the last video. The thing what is still left to improve here is making sure that the load collectors are not already existent. Because for right now, you just could or should execute the command script builder write TCL SPC and write TCL load once, because in this command here you see that there is a load collector created named SPC. Then you have for each node in the list of node IDs setting your SPCs, and this is rather easy because you just have to give exactly what you want. So you see here in analysis constraints, you see the constraint menu. If you select a particular node, for example this one, and then you select something like this and put maybe a 12 in it here, you could do something like that by specifying the different DOFs, like here. So every DOF which is unchecked should have the value minus and 6 nines, and every other would be active. So 12 should be 12, and you see that here I select it to be 0, 0, 0, 0, 0, and a free DOF. So this will be the same as something like this. But I could have any other SPC here. But you see, the problem is if I want to have different SPCs, I would want to call this multiple times, and therefore I should need a check if a load collector already exists. And I will do that, and also maybe put in a separate load and constraint class to deal with that. And I think that would be the best way to do it. And that's on my to-do list. Right. And the same goes for the loads. It's the same thing. You create a load collector. Oops. What? Right. Here we are. Sorry. So here, loads, create entity load collector named loads, and then you create a mark of the nodes you want to apply the load on, and then you just create a load, create on entity curve, and here you have the force x, y, z values, and again, I think the first 3 values are for the direction, and the second 3 values are for the amount. So you have to give it as a fixed vector. And yeah, there's multiple things to do here, so maybe a custom system and stuff like that, but yeah. It's easy, and I think that's good for the starting. And then we have write TCL load step, which basically combines the two together, and here you see also, that's not very nice, SPC and loads are hard-coded here as names. This will be changed in the future, that you have this load collector class, and it will recognize what the names were at the beginning. So this I will fix pretty soon, and we'll just create a static load case and assigning the 2 load collectors in the correct positions, and that's about it. Yeah. Right, so creating load steps, and then I did a basic topology optimization, which is just using the min-mass function for right now, and a displacement constraint. And the displacement constraint you have to give here as a node ID, because that's the node or node IDs, a list, could be multiple. On those nodes, the displacement constraint is active, and this is the amount of displacement which is allowed as max. And it's taking the sum of the displacement, so all 3 components, so the total displacement. And this is just using the property which you have assigned also here. Has to be done better in the future, not hard-coded names like that. And you have the mass, you create a response named mass, and then what's here? For the line selecting the nodes, you have to create an array which has all the different node IDs where you want to impose the load at the deflection constraint or displacement constraint. And so you have to build this string. So it starts with create array, and this is an integer array. So here you see an example. So 8 is the length of this array, and here you have 2 nodes and 6 values. What they are, I don't know really. Should look that up in the Hyperworks help, but at the moment I really don't care much. And this number is just 6 plus the number of nodes. So you see here somewhere length of the node IDs for the deflection constraint plus 6. And for each node, you will add to this line a space and a node ID. This is basically it. Then you have a double array, which the following command wants to use, and just the 6 zeros. And here also you have to reference again the length. And that's about it. Yeah. Here you have the max reflection you want to allow. So this is the D constraint. And I also included, but not used it at the moment, a min compliance topology optimization routine to do that as well. So this takes as an input a maximum volume frag you want to allow as a D constraint, and it minimizes the compliance, the total compliance of the model. Right, and what's left here is just write script and run, which is this. And this writes out the TCL command file and then runs it with the Hypermesh starter command, which I covered in the last video, but just for the sake of completeness here, it's just running the Hypermesh exe, which is here. So for Linux, you would have to change this. It's not doing that at the moment, but I don't have a Linux system here right now. But we could do that in a future video. And it's just using the user profile OptiStruct, maybe a B flag for bash. Batch, sorry, not a basic shell, no, it's a batch execution, and TCL is the flag for the TCL path you want to give that Hypermesh knows what to execute with your model. So that's about it. That's a little bit more in-depth look on what the script builder is doing. I hope you liked it and maybe learned a thing or two. And yeah, thanks for watching again, and I hope to see you back when the code is a little bit cleaner, and I hope to get a little bit of a better result next iteration. Thanks again, and have a good day.